So good afternoon everyone. My name is Kaushik Mahanta and I am honored to introduce the speaker for this session. It is my pleasure to introduce Professor P. Vamsi Krishna sir, who is currently working as a professor in the Department of Mechanical Engineering, National Institute of Technology, Warangal, India. He is having 21 years of experience in teaching and research. His research interests are application of solid lubricants in machining process, application of eco-friendly nano-cutting fluids in machining, vibration-assisted machining, modeling and simulation of manufacturing process, and composite materials. 5 students were awarded PhD and 5 are pursuing PhD guidance under his guidance. He guided 35 postgraduate and 19 undergraduate projects. He completed 5 funded projects and 1 is ongoing. He published 1 textbook, 3 textbook chapters and edited 3 books. He published more than 130 research papers in reputed journals and conferences and 1 patent. He is editorial board member for 10 journals and delivered 35 guest lectures. He is recognized as one of the top 2% most influential scientists in 2022 Stanford University list. He is awarded with Outstanding Reviewer Award by Tribology International Elsevier in 2017 and Best Reviewer Award from Transaction of Indian Institute of Metals in 2020. And now, I welcome Professor P. Vamsi Krishna sir to please come on the stage and start with the presentation on the topic nanomaterials for cooling and lubrication. Please have a big round of applause for sir.
Related to mechanical engineering because it is based on the machining process. Okay. So how we use these nanomaterials in the machining process as a lubricants and coolants. That is one case study I will take and I will explain. So here I think already you have gone through different lectures. Already you know what is nanomaterials, nanoparticles and nanopowders. I need not explain. But anyway, so normally here we consider any of the zero-dimensional nanostructures which are having less than 100 nanometers is considered as a nanoparticle or nanopowders. So then here the next class is nanofluids. That means if you use these nanoparticles or nanopowders to prepare a fluid, then we can call it as a nanofluid. So that means we have a base fluid like any of the oils or maybe water or some other alcohol or glycides, etc. Then we take some nanoparticles and we mix these nanoparticles into the base oil. Then we prepare the nanofluid. So this nanofluid normally we use in different applications like as coolants in radiators or maybe heat exchangers or in different applications. But here we consider this as a cutting fluids. So this is the what we consider here we use as a cutting fluids. So normally we take different nanoparticles that is like carbides, metals and their oxides or maybe carbon nanotubes, and we mix into different base oils, then we prepare the nanofluids. So as you know, already you studied about the basic things about these nanoparticles, like which are having more surface area, right? and also very small particles, and we can able to mix more number of particles into a small quantity of the or small weight of the material gives large number of particles, right? So before going to this application, first we should understand why we require this nanofluids in the machining, right? So that is what very important. So all of you know, right, of course you may or may not be having the background of mechanical engineering, but it's okay. So we manufacture many of the components by many processes, right? So if you take this table, we manufacture by some process, or if you take any of the thing, this fan or AC, everything we manufacture by different process, right? And also the each product is not a single component, right? So if you suppose you take this pen, this is a combination of so many individual components. So we have this button, cap, bottom, and inside refill, right? So ink, everything is there. So what we can do is we manufacture the individual components and then we assemble these components to get the required functionality, that is nothing but a product, right? So and also all these components we manufacture by different process, like casting process or welding process or maybe forming process or machining process, and nowadays we are using additive manufacturing, etc., etc. So basically in machining process we manufacture number of components, right? So this is a majorly used process in any of the industry, okay? So machining is the majority of the cases we use the machining process. Like for example, you want to make the door, right? So we can take a wood and we cut the wood into required dimensions, and then we give design and we give finish, etc., right? So similarly, any of the things, if you want to make a holes into that wall, then we use a drill bit, okay? Like that we use machining for many of the applications in many of the cases, okay? So in this machining process, actually what is our final requirement is, any of the product what you are manufacturing, that product quality should be good. But how can you define a quality? It depends on the product, right? Suppose you take your two-wheeler, then how can you say the quality is good? Depends on the mileage and depends on the stability, right? And depends on the safety. Or if you take your four-wheeler also, same thing, how much mileage you are getting, and if any accident is happened, what is the safety, and also what is the lifetime, etc. Like that, if you take any of the product, the quality is different. Suppose you take your AC. So how can you say the AC quality is good? Less power consumption, and also the lifetime. How many years we can use this without any problem? So sometime we use 5 years, sometime we use 10 years, or sometimes maybe we can use 20 years also, right? So if you see, maybe nowadays if you think about TVs, right? Previously in olden days, if any repair we are getting to the TV, we can replace that component. But nowadays we have to change the total component because we are getting a integrated picture tube, everything. So the lifetime may be less, even though the quality, the picture quality is good, or you are getting a bigger size, etc. But the lifetime may be less. Like that, depends on the product, the quality of the product is different. Sometimes we can say the quality good means it may be a lifetime, it may be a power consumption, less power consumption, it may be a look. Suppose you are purchasing some chain, gold chain or earring, then how can you see? So maybe appearance is good, right? So then we require good design, good finish, etc. So like that in machining process, if you are manufacturing any product, then the quality is important. So here the quality means normally what we consider is the dimensional accuracy. Why? Because we have to assemble the individual components. If the dimensional accuracy is good, then only we can assemble these components. See, you can see sometimes maybe if you purchase a pen, after a few days itself the cap may be very loose. Okay, sometimes the cap may be breaking, right? You observe that one. So maybe if you know the Montex pens, the transparent pen, very drawback is the cap is easily breaks, even though the quality of the refill, the pen is good. So like that, what is happening here? Because of the dimensional accuracy is not good, then we are getting failure of the component. So we required good dimensional accuracy and the surface quality also. Sometimes we required a better finish, right? If the finish is not good, then also the friction may be more, and then we lose the product lifetime, like that. So normally in machining process, what we consider is, if the dimensional accuracy is good and the surface quality is good, then maybe the quality of the component is good, individual component is good, then like that if you assemble number of components, the final product functionality may be good. Because if the number of components quality is good, then only the functionality is good, right? So sometimes you can purchase a cooker, right? So in the cooker everything is good, maybe for example it looks good, the quality, everything, but if the safety valve is quickly damaging, you observe that one with some type of models, right? Quickly it damages, right? Then we have to replace it, like that. So in each product, each component is good, then only the quality is good. Okay, right. So now we consider in the machining, normally generally the dimensional accuracy should be good, surface quality should be good, and the total manufacturing cost should be less, then only the process is efficient, right? Okay, so now we see why or when the surface quality is good. So we can say this one in two types. One is the finish may be good, or the finish reciprocal word or word is rough. So if the finish good means roughness is less. If the roughness more means the finish is less. So we use these two words simultaneously, don't confuse. So here in any of the machining process, this surface finish or surface roughness is depends on number of factors, like that is the first one is workpiece material. So what type of material we are machining, it may be wood, it may be aluminum material, or it may be steel, or it may be cast iron, or it may be some other hard materials like tool steels or alloys, etc. And sometimes this also depends on the cutting conditions, like we are running the machine at a higher speed or at a lower speed, or sometimes whether we are giving more depth of cut or more feed or not. That is nothing but, for example, you are running a two-wheeler, like you take a small Activa. So if you are running that Activa maybe at 40 kmph or 50 kmph, it may go smooth. But if you go beyond 70 or 80, you feel that vibrations, right? Of course, it also depends on the road condition, right? And also weight of the person. Okay, like that here also the machine also depends on, the machining also depends on the speed at what we are running the machine, as well as how much amount of material we are removing, like that. And then other one is tool variables, that is what type of cutting tool we are using, whether the tool condition is good or it is worn out, that is it is a blunt tool or it is very sharp, like that. And other thing is the lubrication condition. That means whenever the machine is running, right, so then the heat will be generated, right. All of you familiar with this one. If you rub any of the stone on the surface also, you can feel that heat, right. So like that here, when you are cutting the material, the heat will be generated. So that heat will be transferred to the cutting tool as well as the workpiece material, or that is nothing but the product. So for that reason, to reduce the heat generation as well as already heat is generated, to remove the heat we require the lubrication and cooling action. Okay, so that is what this lubrication or cooling is going to influence the machining process. Okay, so that is like maybe we use the lubricant as well as coolant in your vehicle also, right. So the lubricant is used maybe to run the different parts of the engine smoothly, but at the same time the coolant is used to cool the radiator or engine, like that. So like that, similarly in the machining also we want the cooling action as well as we want the lubrication action. Okay, we will see here why we required both. That is what important thing. So actually this is the cutting process. Like we have the cutting tool here. So the tool is cutting the workpiece material like this. So here the chip formation may takes place. Okay, so what is happening is, here there are three zones. This is one zone, this is other zone, this is the third zone. So we can say this one is a primary deformation zone, and this is secondary deformation zone, and this is a tertiary deformation zone. So what is this primary deformation zone is, here the chip is removed from the material, right. It's nothing but simply you remove the skin of a banana or skin of any fruit, like that. So we are removing some amount of material from the workpiece, but with the help of a tool, where sometimes you use knife, similar to this one. So then what will happen is, here in the primary deformation zone, actually what will happen is, there is a elastic plastic deformation. Because of that one, the heat generation will be there. So what is this elastic plastic deformation, right. So for example, I want to move this stool, right. So if I apply a small force, for example with my single finger, I may not move. Why? Suppose this table is there, I want to move it like this. So simply if you apply a small pressure, you cannot move it. Why? So it offers resistance. It is having some weight, right. So we cannot move that. So but if I apply more pressure, then I may move it. Of course, if I apply more pressure also, I cannot move this one. There are conditions applicable, but for example you take any chair of that single chair. If I apply a small force, I may not lift it, but if I apply more pressure or more force, I may lift it. Why it is not moving initially? Because there is a resistance from that chair, that is nothing but depends on the weight of that body. So if whatever force I am using is more than that, then only I can able to lift it. So similarly here, any body has its internal energy and bonding strength, right. So if I want to cut that material, it offers resistance. Okay. So if the force applied by us with the help of a tool is less than the resistance offered by this material, then we cannot cut that material. If the force applied by us is more than the resistance offered by that material, then only we can able to cut it. So what will happen is, once the force is more than the resistance offered by that one, then also the material is taking first elastic deformation. Are you studied stress strain diagram of metals? Maybe even though if you are not mechanical engineering, in the first year BTech you studied about that one. So if you see that stress strain diagram, right? So it is going like this and like this. So up to certain level it is a straight line. That means stress and strain are proportional. It's nothing but that region is called elastic region, and then plastic region, and then the fracture takes place. So here also same thing. What will happen is, if we apply a force, then it will deform elastically. Do you know what is elastic deformation? If you take a small rubber band, if you apply a pressure or force, and if I leave it, it comes to the normal state. That is nothing but elastic deformation, right? But if you take something else, then if you are applying pressure and leave it, maybe you take roti, making of roti, chapati, right? Then if you apply a pressure, or you can apply a pressure, it will spread. If you remove the pressure, it will not come back. That is plastic deformation. Okay. So any material, if you apply a load or force on that one, initially subjected to elastic deformation, and then plastic deformation, and then fracture takes place. That means separation of the material takes place. So that is what happening in the primary deformation zone. Okay, right? So then after the chip is formed, it will flow like this on the tool. That is the rake surface of the tool. So when the chip is moving on that one, again here, because of this surface which is having some coefficient of friction, so all this tool and chip are subjected to friction, I mean rubbing action. Okay. So again here also, in this total region, up to certain extent it is called as sticking zone, and some part is called as a sliding zone. That means the first half is having high temperature because the material is just separated from the raw bulk material, so which is having more amount of heat, and which is at a high temperature, and then the second half is a slightly low temperature. So that is why at high temperature the metals are having the nature of welding, right? All of you know welding. So how can you weld? You can heat the metal and then joining. So same thing here. We are not heating, but intentionally we are not heating, but because of the process the temperature is high, and there is a temporary weld takes place between the chip and the cutting tool. So then it is called as sticking zone, and then we have a sliding zone. So here, because of the friction, then here we have only plastic deformation, because this material is already subjected to elastic deformation and shearing takes place. Then there is no elastic deformation, it is having the plastic deformation and then friction. Because of these things also the heat generation is there. So in the primary deformation zone, the heat generation is because of the cutting of the material, that is separation of the atoms and molecules or bonds, and in the secondary region or secondary deformation zone, the heat generation is because of the rubbing action and because of the coefficient of friction. Okay. And then coming to this tertiary deformation zone, then the tool surface is maybe slightly touching on the already machined surface. So then because of the coefficient of friction, again there may be a little heat generation is there, right. So in the primary deformation zone, the heat generation is because of the material property, okay, that we cannot change, we cannot stop it, because if any material you are cutting, there may be, you require some energy and there is a bonding strength between the atoms or molecules or something, then it generates some heat that we cannot change because that is a material property. But in the secondary deformation zone, if you are able to reduce the coefficient of friction, then maybe you can reduce the heat generation. And if you are able to manage the sticking and sliding nature of that surface, right, because already it is at high temperature. So if you are able to cool it quickly and if you are able to reduce the coefficient of friction, then what will happen is we can able to reduce some amount of heat in the secondary deformation zone, as well as the same we can able to reduce heat in the tertiary deformation zone. So what we understand here, to reduce the friction we want lubricant, okay, and already heat is generated in the primary deformation zone. So to cool that tool or chip or whatever heat is generated, that you have to remove quickly, so that we can able to reduce the coefficient of sticking and sliding nature. So that is why in any machining process, I am showing here just example of single point cutting tool, but you take any machining process, it may be drilling or it may be shaping or milling or any process, when you are cutting the material, the heat generation is there and we required the coolant as well as lubricant, that is to reduce the heat generation in the secondary deformation zone as well as to quickly dissipate the heat generated in the primary deformation zone. So why you have to reduce this heat generation, or why you have to quickly extract the heat generation? If you don't reduce the coefficient of friction, or if you quickly don't dissipate the heat, what will happen is the tool will be damaged. Because of high temperature, the tool will be damaged, and also because of this chip formation, sticking action and here, the total workpiece quality may be slightly damaged. So why tool is damaged? You know, any metal, if you heat it, the strength of the metal is going to decrease. That is why sometimes if you are not able to bend it, we can heat and bend it. Am I right? All of you know. So similarly here, when the temperature is increasing, the strength of the material is going to decrease. So the strength of the tool is decreasing. Of course, strength of the workpiece also decreases, but here the tool is there in the machining zone, and also the volume of the tool is, or the area of cross sectional volume of the tool is very less compared to the workpiece. That is why the tool will be more affected, and then it is subjected to tool failure. So which obviously damages the quality of the workpiece as well as dimensionally and surface quality, etc. So that is why in any machining process we required the cooling and lubrication action. So normally we, of course, this is what already I told you, tool wear is there. Tool wear means the tool failure will happen. So because at high temperature the material loss taking place because of the diffusion, because of other phenomena, so the tool failure may happen. So that is why in any machining operation we use a cutting fluids. Okay. So the cutting fluid function is, it should act as a coolant as well as it should act as a lubricant. Okay. So but what is this cutting fluid? Sometimes we use only water, but water is a good coolant, but it is not lubricant. The viscosity of water is almost zero, right? Otherwise, then if you take any of the oil or grease, etc., so then if you are applying oil, it is a good lubricant, but it is not a coolant. So if you want both cooling action and lubrication action, means we want to mix water and oil. So we mix water and oil, but normally, if you drop some coconut oil or something in water, it will not mix. Why? Because H2O molecule is stable, right? And the structure of these oils is different, so which will not mix. These are not solvent. This is not solvent. So then what we can do is, actually here we use some chemical or which is called as a surfactant, right? So into this one. So what will happen is, this surfactant will break the H2O molecule into H plus and OH minus ions. So once this water molecule is breaking into H plus and OH minus ions, it is not stable. The lifetime of this one is very less. But once you break that one, this H plus and OH minus ions, then only these ions will mix with any of the oils, and then it gets like a solution, and then it is having both cooling and lubrication property. So that is why in the conventional cutting fluid, normally we mix water and oil and a surfactant. So we prepare the cutting fluid, and normally we use that cutting fluid in any of the machining operation. So this is what in the olden days, that is basically. But after that, everyone realized that these cutting fluids are not eco-friendly. Why? Because suppose you see in the drainage, right? Normally in the drainages, what will happen? Many of the mosquitoes will be there. So many any of the disinfectants are there. I mean, infectants are there. Many microorganisms will be developed, etc. Right? So why? In the drainage also only water only flowing. But not only water, we are leaving so many things into that one. Maybe whatever we use in our bathroom or cleaning of our house, etc., etc., everything. So there will be a detergents, there will be so many oils, etc. So that is why in the drainages, the water molecule is going to break, and which is not stable. That's why it is the origin for so many things. Okay, so many microorganisms will be developed, and biocides like that. So many chemicals will be there. So actually what will happen is, these are going to create environmental pollution, right? That is why actually many of the chemical factories, if any of the chemical factory waste, if they mix into any of the river or water, the water will be polluted. Even it is simply leaving to the outside, then the soil also polluted. You cannot go for the cultivation near to that one. Why? Because the same thing. So many chemicals are coming out. Again, water and these chemicals are mixing, and which will not be environmental friendly. So these disposals are creating diseases to the workers, and spoils the air, spoils the water, and soil also. So we cannot use the water, we cannot use the air, and we cannot use that soil for cultivation, etc. So all these are the drawbacks. Of course, the cutting fluid amount is small, but the effect is similar to this any of the chemical factories or pharmaceutical factories, etc. But there is a factory, so then the volume is more, so we can see the effect quickly. But here with cutting fluids we cannot see, but the effect is same in a longer period. So because of this one, normally the research is towards eliminating this conventional cutting fluid. So then what are the alternatives? So then we have these are the environmental effects of cutting fluid, that is what already I told you, right? So then what are the alternatives to this cutting fluid? There are so many alternatives, like we can use cryogenic, so which we cool the machining environment at very lower temperatures, and then we use a solid lubricants. So you know cryogenics, right? Maybe liquid nitrogen or something at very low temperatures, so that the heat will be dissipated very quickly. That is advantage. Cooling will be better. And we use solid lubricants. Do you know what are the solid lubricants? Graphite or boric acid or molybdenum disulfide, like that. There are so many solid lubricants. All of you know, maybe at least all of you know boric acid. Can you tell where we use? Yeah, we use powder on the carom board, that is boric acid. Why we are using that? That is same to move the striker freely, that is to reduce the friction. That means it is a good lubricant, right? So like this we have different solid lubricants to reduce the friction, but here the cooling action is not there. We have a lubrication property good, so the cryogenics are having one good property and solid lubricants are having one good property, but both the properties are not there. And then we have vegetable oils which are extracted from plants or vegetables, where these are good for biodegradability, right? We don't have any issue like with petroleum based oils are not good, but however the vegetable oils are good. But at the same time the vegetable oils are having more viscosity, right? Maybe acts as a good lubricants but not be a coolant. So then we have another concept of minimum quantity lubrication in machining. That means we use the cutting fluid or maybe oil or something, but in very small quantity, so that we can able to reduce the pollution. Because in the conventional cutting fluid, maybe per 1 minute we can supply some 500 ml of cutting fluid, like that. It is a flood coolant. But here in MQL, maybe for 1 minute you can use 5 ml or 100, 10 ml, like that. But what we are doing is in MQL, we are mixing this cutting fluid or oil into air along with a compressed air, and we are sending into the machining zone. So it's like a spray, so that it will be better effective even with low quantity, right? That is one advantage. And but what is happening is, again in the minimum quantity lubrication there are drawbacks. Is the quantity what we are sending may not be sufficient for cooling action, may be sufficient for lubrication sometimes, or sometimes may not be sufficient. Then by seeing all these things, the other category is nanofluids. That is what one of the alternative to the conventional cutting fluid, to avoid all these drawbacks and also to get both lubrication and cooling effect. People are used nanofluids, and the research is going on, right? So then from the nanofluids, again the hybrid nano cutting fluids also evolved, right? I'll tell you what is hybrid. So these nanofluids are used in along with the minimum quantity lubrication, so that the quantity is less and the nanofluids we are using. But why nanofluids are useful even though at minimum quantity is, already maybe you might be knowing based on the previous classes. So these nanofluids are having high thermal conductivity, right? Are you know? Not. Because in the base oil we are adding nanoparticles, so the solids are having the more thermal conductivity. So because of the mixing of this one as well as high surface to volume ratio etc., then we are having high thermal conductivity, right? And also we are going to increase the viscosity, right? And also if the nanoparticles what we are using are again a solid lubricants, then we get the lubrication action also. Like that, by mixing different nanoparticles we get advantages of this lubrication, cooling etc. compared to the other alternatives, right? So this is what actually the application of these nanoparticles or the nanofluids in the machining. So then making of these nanofluids, so people are using so many different types of nanoparticles like Al2O3 or TiO2, SiO2, SiC etc. So these are all, some are metal oxides or metals or non-metals etc. And also people are using carbon nanotubes, that is again single wall carbon nanotube, multi wall carbon nanotube etc. So all these are nanoparticles are mixing into a base fluid. So that is again we have two types, two methods in the one step method or two step method. In one step method directly we go for a chemical reaction and we prepare the fluid that itself contains the nanoparticles, and in two step method we prepare the base fluid separate and nanoparticles separate, then we mix. Okay, that is a two step method. And the next one is hybrid nanofluids. What is this hybrid nanofluids? In the nanofluids normally we mix any one type of nanoparticle into the base fluid, but if you mix two or three different nanoparticles into a nanofluid, then it is called as a hybrid nanofluid. Why? Because for example you take some metal, so these metals are having high thermal conductivity. So if I take CuO or TiO2 etc., if I mix these metal oxides into any of the base fluid, then the thermal conductivity will increase. But that means if the thermal conductivity is more, it is having the more capacity of absorbing the heat. Okay, but what is happening? The lubrication may not be good. Of course, the base fluid is having anyway has its own lubrication. Suppose I want to improve the lubrication also, then if I mix a nanoparticles of solid lubricants like boric acid or MOS2 etc., this type of solid lubricants if I prepare as nanoparticles and if I mix that nanoparticles into any of the base fluid, then what will happen? The lubrication will be good. Why? Because these are the solid lubricants as well as already base fluid is having some lubrication capacity, so it will be good. So if I want both, then I will take some both the nanoparticles and I mix both the nanoparticles into the same base fluid. But how much percentage we have to mix? And then the stability of the nanofluid is also very important. So that's why we have to check all these things. So we take vegetable oils, right? Why? Because again vegetable oils are biodegradable. So that's why we take vegetable oils. And normally these vegetable oils are having fatty acids which are normally two types, saturated and unsaturated type. So this saturated fatty acid contains all single bonds, whereas unsaturated fatty acids contains a double bonds. Why? Because the strength of this fluid, base fluid, depends on this either it is having only single bonds or double bonds, as well as and also depends on the length of the bond, that is between the carbon atoms, that is the length of the carbon chain is different in different fatty acids. So for example, if the less than 8 carbons are present in called as a short chain fatty acids, or from 8 to 14 carbons it is a medium chain, or maybe 16 or more carbons contains long chain fatty acids. So like that, what vegetable oils we are taking, whether it is saturated or unsaturated, and what type of fatty acids are there, and also and what type of carbon chains are there, whether it is long or medium or short, like that, based on this combination also the stability is going to change. So then like this, if you see, this is one just example case study. So if you take 3 vegetable oils, right, sesame oil, mahua oil and neem oil, then these are the properties of vegetable oils, that is iodine value, pour point, cloud point, and kinematic viscosity, flash point and density. So here one more property we required, the flash and fire point of this vegetable oil should be high. Why? Because the temperature is high in the machining process. So if the flash and fire point are less, then there may be a chance of burning or maybe quickly losing its properties. That's why we required more viscosity, more flash point and fire point, etc. And then if you see the chemical composition, here we can see each vegetable oil has some percentage of saturated fatty acids and some percentage of unsaturated fatty acids. So you can see this one, this is palmitic acid, stearic acid, oleic acid, linoleic acid and linoleic acid. So normally we consider this one is more important for the cutting fluids. Okay, in this application we consider oleic acid, so that what will happen is the structure may be like this. Okay, so it is contains mostly single bonds. So we have saturated fatty acid and the length of the chain is also important, right? So then selection of the nanoparticle, right? So here also we have a lot of availability is there, then depends on our application we select the nanoparticles. So here I want both cooling and lubrication. So normally among the available nanoparticles, CNTs are having a high thermal conductivity. So if I take CNT, then I can able to get high thermal conductivity, so that it acts as a better coolant, right? So it absorbs more amount of heat from the machining zone. And then if I take MOS2, this is one of the solid lubricant. Of course we have different types of solid lubricants are there. Among that solid lubricants, MOS2 is the one of the better one. Better one means it withstands high temperature, right? And also the coefficient of friction is less, so that the stability is more. So why it acts as actually solid lubricant is, actually if you see the structure is like this. Okay, so this is like a one plane, this is other plane, this is other plane, this is so between the planes the bond is very weak, but within that plane the bond is very strong. So if between these two surfaces, if you are keeping this solid lubricant, when you apply like this, it will slide very easily, because the top layer is sticking to the top body and lower layer is sticking to the lower body, so that the sliding action is very easy. That is why it creates a low coefficient of friction between the two moving bodies, right? And then this CNT is having maybe single wall or double wall or multi wall, like that. So these are having a fullerene like structure like this, right? So then if we mix these two, okay, there is a possibility of getting both better lubrication and cooling action. So that is why, suppose if we are selecting this one in one application, and then before going that we need to understand one more thing, nanoparticle functionalization. So what is this nanoparticle functionalization? So directly we cannot mix the nanoparticle into all the fluids, all the things. Why? Because here some of the materials are hydrophobic materials. So what is this hydrophobic material? Anyone know? Huh? So this hydrophobic material, it's nothing but it reacts with water and maybe it acts as a solvent. That means actually here what we want is the nanoparticle should not solve into this base fluid. It should be like a suspension. Okay. So if it is solving into that, it loses its properties. So it should not solve into that one. But if it is hydrophobic nature, then there is a possibility of solving this nanomaterial into the base fluid. That is why we can check that one, and then we can go for the functionalization. That means we change that nature. So the nanoparticle surface is functionalized like this. Okay, so we use AZ, and then we make the functionalization. There is a process for functionalization. So then what will happen is, every nanoparticle is formed like this. The surface is functionalized with some other material, right? Then it will not solve into the base fluid or solvent. So here this is the nanoparticle functionalization procedure. That is we use H2SO4 and HNO3, and we repeat, we wash this one into that procedure is there. Then we can wash it through this mixer, reflux it, and then we can go for filtering, and then we dry it. Like that we change the surface nature of this nanoparticle. So these are called functionalized nanoparticles. So basically the CNTs may be having that nature of the hydrophobic, right? So that we can go for the functionalization. So that we check the XRD, that means after functionalization any properties are changed or materials are changed, etc. So and we have to ensure that it is still as a CNT. There is no chemical reaction between the functionalized materials and the original nanoparticles. Okay. So then we can form a nanofluids, that is these functionalized nanoparticles we mix into base fluid in a two-step method, so that we can make a nanofluid. That is what so we take a base fluid like this, and then we mix nanoparticles into particular ratio, maybe 1%, 2% like this. So we use the ultrasonicator, so that otherwise we cannot mix normally, because nanoparticles cannot mix normally because of high number of particles. So we use the probe type sonicator or maybe bath type sonicator, etc., anyone, so that it rotates with a high frequency and high number of rotations, so that we get this one. And then like this we prepare the nanofluid, and this is the one, while preparing this nanofluid or hybrid nanofluid, so how much amount we have to mix, that is what important. So here the base oil, we took 3 base oils because we don't know which combination works better. So based on the basic properties of the vegetable oils, we took 3 base oils, that is sesame oil, neem oil and moho oil, and then we took 3 surfactants, right? Because the surfactant also required, because sometimes we cannot mix the nanoparticles completely into the base fluid. So that's why we took 3 surfactants, Triton X100, SDS and Tween 80. Of course these are selected based on the literature. Okay, of course that is already these base oils, vegetable oils are used in different applications, right? May not be this one, but different applications. So there people studied what is the structure, what is the percentage of fatty acids, etc., etc., and like that we get the literature on the each vegetable oil. And similarly we got properties of surfactant also. So based on their properties we selected these things, and then we use the concentration of surfactant in terms of percentage of nanoparticle weight. So how much surfactant we have to mix? So that's why we took 3 percentages, that is 5% of the nanoparticle, 10% of the weight of the nanoparticle and 15% of the weight of the nanoparticle. And then we used this hybrid ratio. That's what I told you. We took two nanoparticles, CNT and MOST. So again there is a question whether we have to take equally or not, or any other ratio, that we don't know. So that's why we selected three ratios: 1:1, 1:2 and 2:1. Right? Of course we can try other ratios also, just we took this one. And then there are so many combinations, so we don't know which combination works well. So we took orthogonal array experimental design, and then we prepared a number of trials, and then this is actually calculation of concentration of nanoparticles, that is weight of the nanoparticle by weight of the nanoparticle plus weight of the base fluid, that gives the concentration of a nanoparticle, right? And like this, after preparing all these nanofluids or hybrid nanofluids, we have to check the stability, right? So stability means whether these nanoparticles are mixing properly or not, and also after a period of time whether the nanoparticles are suspended or coming down as a sedimentation, right? That is what we need to check. So that maybe you can see visually and you can check, but sometimes the visual inspection may not be suitable. So for that one, normally we use a zeta potential value. So for that one we use this type of nanoparticle analyzer is there. So if the zeta potential value is 0 to 30, then this nanoparticle or this nanofluid is unstable. Or if it is 30 to 40, then maybe moderately stable. Or if it is 40 to 60, it is stability is good. Or if it is more than 60, then we can say excellent stability. So after preparing this one, then we can check with the analyzer, then we see what is the stability of this particular nanofluid. If the stability is not good, then maybe we can try with other percentage of mixing or other surfactant, etc. Right? So then these are the tests, right? So this is a sedimentation test. This is after 156 hours. If you observe before going for zeta potential test, just we observe that one, right? So this is what we observe. Some are the particles are coming down and making at the bottom, right? Sedimentation is taking place. So then like that we can observe, so that so here if you observe this one, more sedimentation is there, and here no sedimentation, here also moderate sedimentation is there, and here also no sedimentation. But sometimes even though the sedimentation is not there, sometimes we observe some bubbles or some type of reaction, etc. So which may not be suitable for our cutting fluids, right? So then after that again we verified that zeta potential values also. So where we got a high zeta potential value, that is more than 60, then we got these two are higher values, and again we have some negative values and we have some positive values. Both are okay, right? So then we took these two, right? Of course this is also having the higher value, right? But why we are taken this one is here the base oil is different, and this is sesame oil, so where we got the better value. So that's why we took that combination, right? And then we tried different things like different percentages, different surfactant, etc. Then we analyzed, by using Taguchi analysis, we analyzed at what percentage or at what level we are getting the better values. Maybe here you can conduct more number of tests and you can generate more data, and maybe you can use machine learning techniques, etc., so that we can find out the exact values also. Because here we are taking whatever the levels we selected, among that we are taking. It is 1:2% or 2:1%. It may not be exactly 1:2. It may be fraction also, right? So that if you conduct more number of experiments, maybe you can get the more data, so that we can optimize with any of the optimized algorithms or machine learning techniques, etc. So then we took the S-band ratios, etc. And finally we got this is the optimum, that is the base oil is SM oil, and the particle percentage is 1:2, that is CNT and MOS2, and then the surfactant is SDS, and the surfactant percentage is 15% of the nanoparticle weight. So like this, then the same thing for confirmation, the same thing again we prepared with same composition, and we tested for sedimentation as well as zeta potential value, so that once we are confirming that, then we are going for machining. So in the actual machining environment, then we are going to use this cutting fluid, hybrid cutting fluid. So then we took a normal lathe machine and we are going for turning operation. So these are the conditions all, what is the cutting speed, feed rate, depth of cut, etc. And we are taking MQL at a flow rate of 10 ml per minute, etc. So then we took the ratio of CNT to MOS2 is 1:2. That means if we take 1 gram of CNT, 2 grams of MOS2 is taken, 1:2 ratio. And then the total this weight percentage in the base oil cutting force, that is here if you see, this is the dry machining, that means without using a cutting fluid, and this is by conventional cutting fluid, whatever I told you, mixing of water, oil and surfactant, and this is the hybrid nano cutting fluid. So this is the cutting force, that is the cutting temperature, and this is surface roughness, and this is a tool flank wear. So we got all the 4 parameters compared to dry machining and compared to conventional machining, we got better performance. And here actually the thing is, more than this performance, the main motto of this one is biodegradability, right? So we have to avoid that pollution or environmental damage to the one, but at the same time we have to check the performance also. That is why these are the performance tests. So these are the cutting conditions we used, and then we got this improvement. Then again here we took some percentage of hybrid nano cutting fluid, but what percentage? If you vary that percentage, then again performance may be varied, right? So then what is happening? First of all, why improvement we got? We need to understand. That is what actually important thing. So this is the workpiece material, this is the cutting tool material. So the workpiece is like this and cutting tool is cutting, right? So whatever I have shown, the primary deformation zone and secondary deformation zone. So in the secondary deformation zone, the chip is moving on the tool. So between these two we want to reduce the coefficient of friction. So how it will be reduced? So like this. So between the workpiece and the cutting tool, actually the nanofluid or hybrid nanofluid, whatever we are sending in the MQL, using MQL, that means using the compressed air mixing with this cutting fluid and sending to the machining zone like a spray. Okay. So now that is what we are sending here. Then this is the bond, this is the actually MOS2, and we have MOS2 molecules are there, and here we have the CNT molecules are there, because these two are not reacting, these are like a suspensions in the oil. So once we are sending between these two surfaces, these are acting like that, and because of this bonding of vegetable oil, bonding of MOS2 and the structure of CNT, etc., these are all formed as a film or a layer, thin layer between the surfaces, and the coefficient of friction is reducing. So because the coefficient of friction is reducing, then the heat generation may be slightly less in the secondary deformation zone, and also because of the high thermal conductivity of CNT mixing with oil, then the heat will be absorbed by this one, right? Of course some amount may be evaporated because of these high temperatures, but we observe the heat so that the heat is absorbed by this hybrid nano cutting fluid, as well as the lubrication is also created between the surfaces. So this is the CNT. So this is actually, if MOS2 molecule is there between the tool and workpiece, and if CNT is there and CNT and MOS2 alternatively are there like this. So CNT is like this and MOS2 is like this. So then because of these alternative layers and etc., then what will happen is the MOS2 particles are like this and CNT is like this. So it's become a sliding action, and then these particles or these layers are going here and here. I think this diagram, do you remember? In the first slide I have shown primary deformation zone, secondary and tertiary. So here we are supplying this cutting fluid. So like this, these nanoparticles are going into secondary and tertiary deformation zone like this, and then the sliding action is creating. Okay, and also here we are supplying this one, here between the chip and the tool, between the tool and the workpiece etc., we are able to satisfactorily send this hybrid nano cutting fluid with the help of this MQL equipment, so that we can able to reduce the coefficient of friction, and also we can able to improve the heat absorption, that is extracting the heat from the machining zone. So then this combination, that is sesame oil based, the combination of CNT and MOS2 hybrid nano cutting fluid are proved to be stable based on the sedimentation test and zeta potential test, and then the same thing we used in the machining, that is the 1:2 ratio of hybrid ratio, as well as the SDS surfactant. What is SDS? Huh? Sodium? So what is sodium? D means? This is sodium disulfide. Okay, so that one is better. So then we improved the machining performance. So then this is the actually we are using, that is again the concentration of hybrid nanoparticles we can calculate like this, and again this concentration we can vary. Previously we used only one weight percentage, right, and now within weight percentage we can change, but within this the ratio is 1:2, within this the ratio is 1:2. So we can change the concentration of nanoparticles in the base fluid, so that we prepare the different this one, and then we check the basic properties. Like actually the previous one is just a confirmation test whether this hybrid nanofluid performing better or not. So then after going for different concentration, then we can check what about the viscosity, what about the thermal conductivity, and what about the coefficient of friction, right, and etc. We can check the basic properties, because we want these three, right. We want better lubrication, we want better cooling action, and we have to reduce the coefficient of friction. So like that we check. So we use a rheometer for testing the viscosity, right, and then with the different percentages. Normally it is common, if you are increasing the weight percentage, the viscosity is going to increase. But at the same time here we need to understand one thing, if it is more viscous also, the flowability is decreases, so which is not required for us, but at the same time we want a viscosity. That's why some arbitrary value or wherever we are getting the saturated value, that we have to verify. So this is actually the viscosity, and then we use thermal conductivity, hard disk thermal conductivity analyzer, so that we check the thermal conductivity. So if you are increasing the weight percentage, then thermal conductivity also increases, viscosity also increases. and then this is at a different percentages, the thermal conductivity values, and then this is the coefficient of friction. So we apply the same thing and we can find out what is the coefficient of friction between the surfaces. That is we use the tribometer or pin on disc operators, etc. Then we can find it. So between the two surfaces, actually the hybrid nanofluid will be like this, right? So maybe carbon nanotube, maybe embossed particles. We don't know exactly how this will be, but this is our assumption. If you are mixing properly and you are using the same hybrid nanofluid, we are assuming that these are equally distributed, and so that we get the better this one. That is why we are checking the ratio 1:2 or 1:1 or 2:1, etc. Then here we are getting a low coefficient of friction for this one, for this combination. What is this 3 and 4? That is at 1.5% and 2%. After that, again coefficient of friction is increasing. That is what I told you. The viscosity becoming more and it becomes obstruction for the flowing action. Then again coefficient of friction increases. That is why we got better value at a percentage of 1.5 and 2.8%. Then we have to check this one, which is better in the machining operation, right? So based on this one, we selected the 1.2 and 2.8%. Of course, the lowest coefficient of friction 2.8%. Based on the thermal conductivity and viscosity and this one, we selected finally 2.8%. And then we used again in the machining operation, because previously we tested only at a particular speed, feed, depth of cut. Okay. Then if you are changing the speed, then what will happen? Because if the speed is high, then the heat generation is more. If the heat generation is more, then we require more cooling and more lubrication. So at high speeds, whether it is useful or not, at lower speeds maybe it will be useful, right? So at higher speeds may not be useful. Like that we have to test at different speeds or different feeds, etc. And these different percentages also we verified. So these are the conditions where the nanofluids are performed. So this is the cutting force, right? Different cutting forces, and this is cutting temperatures, right? So this one is having high thermal conductivity, that's why temperature may be less, okay? And here again the cutting force is less for this one, because the coefficient of friction is less. That's why one property may be useful to reduce the cutting force, and other property may be useful to reduce the coefficient of friction, or that is to reduce the temperature. And then if you check the surface roughness, that is surface finish or surface quality, then again 2% may be better. Again slowly it is increasing, because the coefficient of friction is more, and the flank wear is also like this. Of course flank wear may be less, because if it is temperature is less, then the flank wear is also better. So like this we are getting the machining performance of different nanofluids, different percentages, etc. Then we can able to finalize what is the best composition and what is the best base fluid. Like that we can try different combinations. Whatever the possible is there, you can try any one, but this is what within what we are taken, this is the better combination, right? So if you are changing the combination, maybe the performance maybe changes. If you change base oil, or if you change nanoparticle, or if you change the percentage, then the performance may be different, okay? So like that in this case we studied at different machining conditions, different percentages, etc. And finally we come to some conclusion, that is the CNT and MOS2 nanoparticles as 1:2% in sesame oil with the SDS surfactant, and surfactant weight percentage is 15% of the nanoparticle weight percentage, and also 2% is the nanoparticle weight percentage in the base fluid. So this combination is given better performance at all the conditions, okay, right? So this maybe you can try any machining operations or any other applications or any other things, okay. So this is what one application of this nano fluids, that is hybrid nano fluids as coolant and lubricants, right? So do you have any doubts? Please ask me. Yeah, that's what I told you. See, suppose you want only reduction of heat or only absorbing the heat. So we select nanoparticles which are having high thermal conductivity. So maybe CNT is having high thermal conductivity. So then you can go for only single nanoparticle. But here application is we want thermal conductivity as well as lubrication. That's why we go for the hybrid. But some other applications, maybe in the heat exchangers or maybe in the some radiators cooling or maybe in the some micro channels used in the electronic components, etc., like your laptops, if you want to cool, right, there are micro channels where the liquid will be there, okay, high end computers, etc., there we want only the cooling action, lubrication is not required, then we select the nanoparticles which are having high thermal conductivity. Like that, depends on your application, you have to take. And also there I don't want base oils, maybe we can use water, because I don't want any viscosity, I don't want any reducing the coefficient of friction. This is the machining application where I want lubrication also, that's why the base fluid is a oil. That is also especially vegetable oils to go for the biodegradability or eco-friendly cutting fluids. Okay, that is what you have a lot of literature, you can try anything. This is the procedure or whatever, just this one. Okay, so if you have any doubt, please ask me, otherwise we can close this session. Okay, right. So if you have any doubts, maybe you can mail me also later.